Okay, so now we're going to introduce calculus, and the reason why we need to use calculus is this. All these equations we've been using assumes constant acceleration. So every problem that we've done so far in, say, AP Physics 1 or so far in AP Physics C have been constant acceleration problems. We need to use calculus when the acceleration is not constant. Okay, so here's an example. If I have this x equals 40 plus 8t minus 0.2t cubed, it doesn't follow this format here. The t isn't squared, it's cubed, so it's not going to be a constant acceleration problem. I can't use the equations I've been using. So I could do something like describing its motion. So if I graph that function, I end up with this curve, and I could say that from t equals 0 to 4, that about 4, that it is moving in the plus x direction. Maybe it's slowing down gradually. Okay, and then from t is 4 to infinity, it's moving in the minus x direction and speeding up. Okay, however, I want to be able to do things like what is its velocity at any moment in time, or its acceleration at any moment in time. So that's what we're going to start learning how to do. So if I had a position time graph, I would find its average velocity by doing change in x over change in t. It's basically the slope. Now what we do in calculus is we find the derivative, which is the slope at any point in time. So the velocity is going to be the derivative. We'll write derivative as dx by dt. Okay, and that's going to be the velocity at that particular point in time. And acceleration has been delta v by delta t. If it's constant, it doesn't. The slope is it's always going to be a straight line. The slope is going to be constant. That's not going to be true anymore. So the acceleration we're going to find by doing dv divided by dt. Now, how do we find derivatives? Right now, I'm going to show you how to do derivatives for simple polynomials. Later on in calculus, and here we might do it for more complicated functions. But for right now, we're just going to do it with polynomials. Now, the simple rule is this. If I have a function y equals ax to the n power, okay, when I try to find the derivative of y with respect to x, I multiply by this n and subtract 1 from the power. Okay. So I'm going to do 2 examples here. Okay? And I'm going to change this one because I don't particularly care for it. I'm going to make this y equals root 6 minus square root of t. Okay? Now, looking at this, the first one is x is 4t squared plus 6t minus 6. Okay? I'm going to make a note over here. T is t to the first power. And t to the 0 power is 1. Now, my dx by dt is I'm going to take the power over here, the 2, and multiply it out front. 2 times 4 is 8. So I get 8 with t, and then I subtract 1 from the 2, and I get 1. Plus, remember this t is t to the first, so 1 times 6 is 6. T, and I subtract 1, that's t to the 0. Now, This is kind of like times t to the 0. 6 times 1 is 6. And when I multiply that 0 out front, I'm going to get 0. And that happens anytime you have a constant. When you take the derivative of the constant, it ends up being 0, and it cancels, so you don't have to worry about it anymore. Now, I did this out in kind of detail. I probably wouldn't write t to the 1. I would just write it as t. And here I wouldn't write t to the 0. I know t to the 0 is 1. 6 times 1 is just 1. So that is my dx divided by dt. So that would be my velocity at any time t. Now, for this one, okay, if I want to find dy by dt, first I'm going to rewrite this. This is going to be y is 6 minus. Whenever I see a square root, I'm going to remember that that's to the 1/2 power, because then I can use my power rule. Okay. Dy by dt. Okay? When I take the derivative of 6, that's a constant. When I take the derivative of a constant, it goes away. I don't have to worry about it. Now I'm going to look at the t to the 1/2 here. I multiply out by 1/2. Now I get negative 1/2 t. And when I subtract 1/2, subtract 1 from that, I get minus 1/2. Now that's a little bit awkward looking because we don't like that negative 1/2 power. So I could say dy by dt is minus 1/2. And then the negative 1/2 power, the half is a square root, and negative means it's on the bottom. So you have the square root of t down there. So that's the derivative of that. Now, applying it to the specific function back here, okay, which was 40 plus 8t minus 0.2t cubed, okay. So the function was x equals 40 plus 8t minus 0.2t cubed. If I take the derivative of that, okay, I have a constant here. When I take the derivative, that goes away. I don't have to worry about it. 8t is 8t to the first. Okay, so if I multiply 1 out in front, I get 8. And then I have t to the 0. T to the 0 is 1. So just like I said, whenever you have a constant, it drops away. The first term, or the t term, the t is just going to drop away. And then my next step is going to be minus 3 times 0.2 is 0.6 t, and then I subtract 1, and I get t squared. Now, if I want to find the acceleration, I'm skipping ahead a little bit. The acceleration is the derivative of that. So a is dv by dt. Okay? Now, this first term in the velocity now, 8, is a constant. When I take the derivative, that's going to drop away. So for the next term, I take this 2, multiply it out front. 2 times 0.6 is 1.2, so minus 1.2. T, okay, 2 minus 1 is 1. T to the first is just t. So now I've found the velocity function and the acceleration as a function of time. Now we got this problem, what is the velocity at t equals 2? So we think this, v of 2 is going to be 8 minus 0.6 times 2 squared. So the velocity at t equals 2 is going to equal 5.6 meters per second. So you can see that this is a pretty powerful technique. I can find the velocity at any point in time. The second part of this, at what time is the velocity of the object 0? So now I'm going to go back to that velocity function. V equals 8 minus 0.6 v squared. And I want to know when the velocity is going to be 0, so I can just set the equals 0. 0 equals 8 minus 0.6 t squared. So if I bring the 0.6 t squared over the other side, 0.6 t squared equals 8. Divide by 0.6, and I get t squared equals 13.3. Okay. And if I take the square root of that, I get that the t is 3.65 seconds when the velocity is 0. Now, if we look back at our graph back here, okay, we said it was about 4. It turns out it's going to be at 3.65, so maybe right about there, where the velocity is 0.